Thank you all for being here. We're going to talk about structured concurrency in Java, specifically what it is and why do we need it. So this entire talk is divided in three parts. First, we will see why we actually need structured concurrency. Why is there a need for it? Then we will deep dive into structured concurrency and see how it is done in Java. And in the last part, we will compare the structured concurrency API with the Complete Well Future API. So yeah, let's get into it. My name is Balkrishna Rawool. I work for ING Bank. And okay, let's start. Let's go way back in time. Let's start with early programs. Early programs were sequence of instructions with some go-tos in between. But the problem with go-tos is that if you have a lot of them, your code literally becomes like spaghetti. The term, in fact, spaghetti code comes from this. Now, the problems there are that your programs, it's difficult to isolate a part of the program from the rest of the program. Also, there is high cognitive load in understanding this, and it is difficult to read and difficult to understand. Now, this was solved by using an approach called structured programming, which was introduced by Edgar Dijkstra. Structured programming introduced these three control structures. So what it did was it prohibited the use of goto, and it introduced these control structures for conditionals, loops, and subroutines, and also made programs easy to read and easy to understand. Now, if you come back to the modern times, the current times, you have concurrent programs. They also suffer from a similar problem. So you have main thread, and then we start a bunch of threads. Now, creating a new thread is like using goto because your control is actually split, so it gets transferred and it also continues in the same continues the same routine as well. But then if you have few threads, it is still fine. You can understand what is going on in the program, you can wrap your head, but if you have a bunch of them, again, they suffer from the same problem as we saw earlier with goto statements. So starting a new thread is like using a goto, and multi-threaded or concurrent programs have the same problems as programs with goto. Now, is there a structured programming approach for concurrent programs? Yes, there is, and it is called structured concurrency. So what structured concurrency does is, it sort of ties these loose ends of your threads, and then it helps you to manage your threads. It addresses the issues that we saw earlier, and the principle here is that a thread or a task, if it is started in a scope, it cancels or it finishes in the same scope. It brings in structure and order to the concurrency aspect of programs, and makes our concurrent programs easier to read and easier to understand. So basically, the benefits that structured programming brought for programs, structured concurrency is trying to bring those benefits for our concurrent programs. So this is why we need structured concurrency. Now, in the second part, we will look at how structured concurrency is done in Java, and for that we have to look at Project Loom. So it is an important project at OpenJDK, and the purpose here is to have easy to use, high throughput, lightweight concurrency and programming models for it. So the core is again concurrency, and the idea is to provide high throughput, lightweight concurrency. And there are three main features in Project Loom. They are virtual threads, structured concurrency, and scoped values. Now, virtual threads are lightweight user threads. Structured concurrency, as we saw earlier, brings in structure for your concurrency aspects, and scoped values are there to address a very specific problem with thread locals. Now, the idea in this talk is to get a sort of idea about the structured concurrency. So we will get in details of that, and for that we'll also get some idea about virtual threads, but we will not discuss scoped values. And yeah, an important thing to mention, Java 21, which was released last month, has virtual threads as a final feature, but structured concurrency and scoped values are still in preview. So the code that you will see, you can run with Java 21 as long as you have preview features enabled. Okay, so let's start with virtual threads, and for that we first have to look at platform threads, or otherwise known as threads, which are present in Java for a long, long time. And what they are basically a thin wrapper over operating system threads. So what does this mean? When you create a new platform thread, your JVM actually requests operating system thread to create a new thread, right? And when that thread is created, it is able to create the platform thread. Creating an operating system thread is a resource-intensive task, so it requires quite some memory, and it also takes some time to create that thread. So, and as you see in the picture, platform threads are sort of one-on-one map to operating system threads. So for every platform thread, there is also an operating system thread. The platform threads offer limited scalability when using thread per request model. Now let's take a moment to understand what this is. So what is thread per request model? Imagine you have a server which is serving an application. And when you get a request, the server creates a new thread to process that request. Now that model is called thread per request model. And when you use that, the maximum number of requests that you can service at given point in time will depend on the maximum number of platform threads you can have, right? And that would depend on the number of operating system threads that you can have. And because operating system threads require significant memory, so you can create so many number of operating system threads, and therefore you create so many number of platform threads, right? So that's why we say that the scalability offered by platform threads is limited. And there is a need for pooling. So because creating an operating system thread is a resource-intensive task, you don't want to create platform threads willy-nilly, right? When you create platform thread, you don't want to throw it away when you're done with it. So that's why we pool them. We put them in a thread pool so that next time when you need a thread, you get it from the pool. Right, so that's with platform threads. Virtual threads, on the other hand, are lightweight user threads. Lightweight, meaning they require significantly less memory, right? And because they require significantly less memory, we can create huge numbers of them, thousands or even millions of virtual threads. Also, there is no need for pooling. So when you're done with a virtual thread, you can just throw it away. So next time when you need a new one, you can just create it. Also, what you see here is that you have a large number of virtual threads, right, and a few number of platform threads. A virtual thread on its own cannot execute anything, so it really requires a platform thread, and that's why some virtual threads are mapped to these platform threads. But then you see virtual threads in large number, right? So how is that mapping being done? For that, we have a new thing called as virtual thread scheduler in the JVM. And what this does is, so whenever a virtual thread requires a platform thread, it attaches that virtual thread to the platform thread. That process is called mounting. So it mounts a virtual thread onto a platform thread. And when the virtual thread does not need a platform thread anymore, it unmounts it from the platform thread, or also known as carrier thread. And that unmounting can happen at a time, let's say when your virtual thread is waiting for a network resource to be available, right? So at that time, it does not require any CPU processing. It does not require platform thread, so it gets unmounted. Okay, so we have seen a few things about virtual threads. Now let's see them in action. Let's see how we can create virtual threads. So I'm gonna head over to my laptop and to Eclipse to create some platform threads. You're able to see my screen, right? And the font is big enough. Yeah? Okay, perfect. So let's create a platform thread, and you probably would have done this in the past. So you create a new thread by passing a runnable to it. And in this case, we just want to print the two-string representation of the thread. So we create a thread like this. Now let me run this. In order to run this, I've created some JUnit tests. So actually, there is a set of JUnit tests which are just wrapping the method that I have. So let me run this method and see what happens. Okay, it creates a new platform thread, and it prints the thread that it has created. With Project Loom, there is also a new API to create a platform thread, and that goes something like this. So thread.off platform dot, not stack size, but start. Then I don't need to call this. Now if I run this, same thing will happen. We have a new platform thread. Now how do you create a virtual thread? Well, actually it's quite similar. But instead of platform thread, we would just do off virtual. And this would create a virtual thread. Now let me run this. And we have our virtual thread. Now what we see here is that virtual thread, this is the ID of the virtual thread. And we also see this part, which is actually the platform thread or the carrier thread, which is being used to execute the virtual thread. Also, you have a shorthand method. So you can simply do thread.startVirtualThread, and that also creates a new virtual thread. So it would do the same thing. And you can even use an executor service. So let me use try with resources. Oh, executors.new virtual thread per task executor. And again, so this is a executor service, but it is not backed by a thread pool. So every time you request a new virtual thread, it just gives you a new instance of the thread. It is auto-closable, so it actually waits for all the virtual threads. So let me just create one virtual thread, executor.submit. It takes a callable. Again, we are going to just print the two-string representation of the thread. So if I run this, same thing will happen. So we get a new virtual thread. But in this case, because it is an executor service, I can create a bunch of them. And it will wait for all of them to finish. So what we see here we have a bunch of virtual threads, and they are running on some platform threads. For some of them, for example, these three, what we see is that we have different virtual threads, but they are running on the same platform thread. So this is what we see, what we earlier saw, that virtual threads are getting mounted and unmounted. So when this virtual thread is done, the platform thread is free to, let's say, support another virtual thread, and then that one gets mounted onto the same platform thread. Okay, so we have seen this. Now move on. Let's see, what is the best way to use a virtual thread? Now, the best way to use a virtual thread is to submit a business or a simple task to it. With platform threads, what we did was that we have a thread created and we submitted multiple tasks to it. But with virtual threads, because they are cheap to create, we just submit single tasks to it. Now, what is the advantage of doing that? That way, you can have multiple tasks and then structure them in a way that represents our business logic in the most logical way, right? Because we have that freedom with virtual threads. Now, doing that is actually what structured concurrency is. So virtual threads enable structured concurrency, because with platform threads, you still have to think about pooling. You still have to manage your threads. But with virtual threads, you don't have to pool them. You can basically create a new virtual thread for every task, and you can structure them in the most logical way. And let's look at some examples. So here what we see is that you have your main task, which is creating 3 subtasks. And when all these 3 subtasks are finished, you're continuing with your main task, right? And then in this example, again, you have 3 subtasks, but you don't wait for all of them to be finished. As soon as first task finishes, you continue with your main task. You can also have a bit more complicated structure of your tasks. So you have 3 subtasks here, but when subtasks 2 and 3 are finished, you create a new subtask, and when 1 and 4 are finished, you continue with your main task. Now, all of these examples can be implemented using structured concurrency. In fact, they can be implemented using structured task scope, the new API that is available with Project Loom. And we will see some examples of these later on. Now, the principle behind structured concurrency is that when the flow of execution splits into multiple flows, then they rejoin in the same code block. Now, what we see here, you have main task and 3 subtasks, and then they join when all of them are finished. They continue with your main task, right? So the implementation of this in the code, that you will see that the fork and join is happening in the same scope. Now, this brings in a lot of benefits, and we'll look at them one by one. So let's start with the first one, error handling with short circuiting. So here you have 3 subtasks, and you want all of them to be finished. But what if there is error in one? You don't want to continue waiting for the other ones, right? So you immediately cancel them, and that is what short circuiting is. That is what structured concurrency provides you. Also, cancellation propagation. So what if your parent task gets canceled? You immediately cancel your child tasks as well, and that is cancellation propagation. So you basically propagate the cancellation from parent to the child tasks. Clarity. So this structure of tasks, when you implement in structured concurrency, this structure is evident in your code as well. So it brings in that clarity, which makes your code easier to read and easier to understand. And observability. So basically what you see here is you have 1 main task and 3 child tasks. Now, each of these child tasks can have their own child task, right? And you can have a nested hierarchy which goes pretty deep. So you have a big hierarchy of tasks, and as we saw earlier, you use 1 virtual thread per task. So what you will do is you will have a big hierarchy of virtual threads, right? And when you do thread dump, you can also get that thread dump in a format that represents that hierarchy. And that is the observability benefit. So in the hierarchy, you see the threads, and then you can point to a specific thread which is causing problem, and then you can fix it. So that's the observability benefit that comes with structured concurrency. Okay, so we have seen quite theory about structured concurrency. Now let's see some action. So what we're going to do is we are going to see different scenarios, different use cases, and for each of them, we will implement it using Completable Future API and also using Structured Concurrency API, and then we will do comparison about how the API works. Let's take a quick look at Completable Future API, just so we have the stage set. So Completable Future API, it provides an API for asynchronous processing, and it allows us to chain multiple stages to create pipelines, and it does so by using callbacks. Right? So let's start with the first use case, which is event management. So what we're doing here is you have 3 subtasks: reserve venue, book hotel, and buy supplies. So when you have all of these things, so when you have your venue, hotel, and supplies, then you create your event. Right? So you have to finish all these subtasks in order to continue with your main task. So let me implement this using Structured Concurrency API. For that, I'll head over to Eclipse. OK, so I already have implementation using Completable Future. So what we do here is we have these 3 tasks: reserve venue, book hotel, and buy supplies. And we are creating Completable Futures for each of them. And then we use all of to combine all these futures. Right? So when you're using all of, you get you get a new Completable Future, which is finished when all of these underlying futures are finished. And that is exactly what we want. Right? And then we do some exception handling, and then we apply, which gives us the results of these futures. And then we use those results to create our event. So this is how you would implement this use case in Completable Future API. Now let's take a quick look at what is happening inside these tasks. So what is event util, and what are these methods doing? Event util actually gives us some stub responses. And for each of these tasks, we call this log and wait. What that does is it waits for a random amount of time, but also shows which thread it is executing, what is the task that is executing, and the amount of time that it is going to wait. So there's nothing fancy going on here, but it is just showing us what the task we are executing. So let me run this. And again, to run this, I have JUnit test. And when I run this, I hope that it works in the way we want it to work. Yeah, so we have these 3 tasks created. They are running on 3 platform threads. And when all of them are finished, we have our event object created. So this is exactly what we wanted our code to do. Now let's see how we can do this with Structured Concurrency API. So for that, we always start with try with resources. And that is because the scope object, or the structured task scope object is auto-closable. It frees up resources when you are done with it. So let me create that. So we create a structured task scope. And structured task scope has 2 subclasses out of the box. And they are shutdown on failure and shutdown on success. You use shutdown on failure when you want all of your subtasks to be finished. And that is what we want in our use case. So we're going to use shutdown on failure. What it means is you actually stop when there is a failure. And when you want all of your tasks to be finished, you actually don't want to continue when there is a failure. That's why we use shutdown on failure. And then what do? You basically fork your subtasks. So in this case, we are going to use these tasks, event util, reserve venue first. And when you fork, you actually get a subtask. And we're going to put that into, let's say, task 1. And then we have 2 more tasks. So we have book hotel and buy supplies. OK, and these are going to be, let's say, task 2 and task 3. So when you have your tasks forked, what you do then, you wait for all the tasks to be finished. You do that by using this join method. And then you see if there are any errors, and then propagate those errors. OK, and then we are basically at a point where all the tasks are finished. And now we can get the results of these tasks. So you do task1.get, which gives you a venue. Similarly, task 2 and task 3 will give us hotel, and supplies. Okay, when you have all of them, you can create your event object, and we're going to just print that. So let me just do that. New event, which uses venue, hotel, and supplies. Okay, so if I run this, I expect that it works the same way that the complete well future example did. So here we have, again, these 3 tasks created. They are taking some random amount of time. But the only difference is that they are running on virtual threads here. And when all of them are finished, we have our event object. And this is exactly what we wanted. In fact, these 2 implementations are now equivalent. The only difference being that one is implemented using Complete Future, and the other is with Structured Concurrency API. And if you compare them, the first difference that you see is that Complete Well Future uses callbacks, right? Whereas Structured Concurrency sort of provides an imperative API. So what you do here is you create a new scope, and then you fork your subtasks, then you join them, and then you get the results from them. So this is pretty imperative. Also, Complete Future uses runtime exception for exception handling. In fact, it throws completion exception, which is a runtime exception, whereas in Structured Concurrency, you have these checked exceptions. So you have to handle them. Execution exception is a checked exception. And then depending on your preference, whether you like runtime exceptions or checked exceptions, it could be a good or a bad thing. And another thing to mention is that Complete Future.all-of, it gives you Complete Future of void. So you end up having an argument which is always ignored. Yeah, so basically those are the, let's say, differences between this implementation and this Structured Concurrency implementation. Let's move on to the second use case, which is a weather service. So here you have 3 sources where you get your weather information from. This question?
Yeah, I have a question actually to the example in slide 4. So of course it works really nice in the case that everything runs through and succeeds. But imagine there's a failure in booking the hotel.
Yeah.
And I would like to then also clean up all the other things that I maybe have observed over here. Is there
Right.
a way to integrate that nicely without having custom logic?
Okay, maybe not without having custom logic, because you know exactly what you want to clean up from the reserve venue or the buy supplies part.
I don't know exactly what has already been completed.
Right.
I'd like to clean up everything that is completed if there is any failure in the whole structure.
Right. So for that, what you would want to do is you would want to extend on the structured task scope class and create your own custom shutdown policy. And that way you get handled to all of these events that are happening within this, and then you can clean up. So by default, what it does is if one of the tasks fails, it actually cancels the other 2 tasks, right? So that is what it does. But then from the business perspective, you don't know what extra cleaning that you need to do. For that, you can write that in your custom subclass.
So it will cancel, of course, tasks that are currently still in progress. But
Yeah.
imagine you have tasks that are already completed, and you would have to handle.
Right. Then you can basically extend this class and create your own custom shutdown policy, and then handle it there. A good question, by the way. Yeah, that should also be possible. But again, I think you are defining a behavior which is very similar to shutdown on failure, but not exactly. So what happens in shutdown on failure is that it basically completes the scope when all the tasks are complete, right? And then what you want is you also want some more space where you want to still roll back, right? Even in that case. Now for that you would again create a custom shutdown policy and then put your logic there. If shutdown on failure meets your requirements, you can just use that. But if not, just extend it and write your own implementation. Okay, let's move on to the second example. Again, so in this case, we have 3 services, and you want the result of only one, whichever that finishes faster. How do you do that with completable future? So here you have, again, these three completable futures, which are for each of these tasks. And you use any of, because you want a future which finishes when any of these underlying futures have finished, right? You use some exception handling, and then you get the result, and then you print it. So let me just run this. Yeah. Again, you see three tasks running on the platform threads, and well, in this case, two of them are finishing exactly at the same time. So source 2 and source 1 are finishing after 2 seconds. So you see both of them getting finished, but the result of only one of them is being used. The other result is ignored. Let me run this once again, just to make sure that we see only one task finishing. Yeah, so here, source 2 takes 2 seconds. That finishes fastest, and then you have whether or the response from that being used. OK, let me do this in structured concurrency API. Again, you start with try with resources. You always create a scope variable, which is going to be a structured task scope. And in this case, we are going to use shutdown on success. Because what you want is when you have one success, you want to stop. You don't want to continue with executing others. You have enough response or enough result to continue with your main task. You don't want to waste your resources on executing other tasks as well. And that is shut down on success. It takes a type parameter, which is basically the type of your result. So in this case, it is weather. And what do we do with that? We fork subtasks. So the first subtask is going to be get the weather from source 1. And then we have other subtasks, so from source 2 and source 3. And then we wait. Let me do exception handling. And then we can directly get the result in this case. And the result is going to be weather. And exception handling. And let's print the result. OK, let me run this and then see that it actually works the way we want. So it creates, again, 3 subtasks. They're running on virtual threads. And again, we see 2 of them finishing at the same time. But result of 1 is being used. So let me run this once again, just to make sure. Oh, again, we get 2 tasks finishing at the same time. Let me try once again. Yes, now we have source 3, which is finishing the fastest. And the result from source 3 is being used here. And other 2 tasks are being canceled. OK, what else? Again, I mean, if you compare the implementations, the differences are in the callbacks and imperative API, also the runtime and checked exceptions. And one more difference is that any of gives you complete feature of object. So even though all of these underlying features are features of weather, the resulting feature is actually feature of object. So this weather is of type object. So your type information is getting lost when you use any of. Whereas in structured concurrency, the type information is retained. So this weather is of type weather. OK, now I have a question for you. We're going to simulate a scenario where we have these 3 subtasks and one of them fails. So you have, let's say, get weather from source 1. It fails, so it throws immediately a new runtime exception. And you don't get any response back. So we have 3 futures. One of them fails immediately. The other 2 will eventually continue and succeed. But we are using any of. What do you think will be the result of this resulting future? Will it error out with some exception, or will it wait for the successful completion of one of the underlying futures? How many of you think there will be an error? OK. It depends. It depends on? The first one, because you immediately get an immediate exception. There will be runtime exception. Yeah. So let me run this, and you're actually right, because it actually throws this runtime exception. But is this something that you want? You actually want a result of the first successful completion, right? So complete future, you're right, it behaves this way, but in my opinion, this is not very logical. Uh, Now, if we use structured concurrency, on the other hand, what do you think will happen? Uh, so it will complete in the logical way. Uh, so it ignores the first runtime exception, and it waits for the next successful completion, and then it prints that result. So in my opinion, structured concurrency behaves more logically than completed future in this scenario. But again, I mean, if you know what is happening underneath, then you can still deal with it. Yes?
It's the behavior you specify, yes, because you say on the exceptionality, just throw exception, yes. So
Right.
that's what you need. That's what you want. You could just swallow the exception, and then you would still wait for another one to complete.
OK.
I think you specified that behavior impact.
Oh, OK. OK. So if I basically remove this, then
I mean, you have to just swallow the exception, just add the exception from
yes, exactly.
if you just comment, leave the rest, but if you
Right.
27.
OK. Yeah. So if I basically don't do anything on exceptionally, uh, then I have to return some logical thing. So I'll have to return, I don't know, some object, new weather, right? This is what it has to be. Or it cannot be, because I think it expects an object. Yeah. So I don't know. Yeah, just return null. That would be the thing, always an escape for us. But catch everything, return null. I think that's the answer to everything. But yeah, so again, I'm not sure if this is the right approach. Right? This is the way that you want your code to be. So that's the thing that like I have a problem with. But again, I think this is a bit more logical with structured concurrency. But as long as you know what is happening underneath, then it is still OK. OK, thanks for the good question. Let's move on to the third scenario, which is a bit more complicated. So here you have a banking portal. And what you do is the customer is waiting for some offer. So you first get the customer data. Then you get savings and loans data concurrently. And then when you have everything, you calculate offer for the customer. Now, how will you do that with completable future API? So first, you have completable future, which is for the task get current customer. Then we have two futures started in an async fashion for savings and loans data. This is because we want them to be running concurrently. You wait for the first future. So you have the customer. Then you combine future 2 and future 3 with the customer information. And when you have everything, then you use calculate offer. Some exception handling, and then finally, you have your offer. Now, let me run this. And then see that it actually does what the picture depicted. So you're first waiting for customer. When you have that, then you start savings and loans data. They are running concurrently. When you have both of them, then you calculate offer. Right, so this is exactly what we wanted. Now let's see how we can do this with structured concurrency API. Again, you start with try with resources, right? But in this case, there's only one task. So you don't want to, like, there is no need for orchestrating multiple tasks. There is no need of waiting for all of them or using only one of them. There's only one task. So you don't really need scope around your task. You could use, but there is no need. But what you do need is a virtual thread. So as long as you are running this thing in a virtual thread, then your underlying platform threads or CPU is not getting blocked. So what you would do is you do thread.start virtual thread. And then you will do this task, which is getting a current customer. And you will put that into a customer object. OK, so this is what we want to do. But then imagine a scenario where you have your server creating virtual threads to process all the requests. So you already have a context which is virtual thread. So you don't want to create a new virtual thread. So you could simply do this. So here you have a blocking call, but we are just making blocking call without having any ceremony or any management of threads around it. This feels a bit weird because I think we are not used to writing this kind of code where you have where you have platform threads, and then you do need to do some management. But because of virtual threads, you are able to call blocking methods as if they are non-blocking. Now, in order to simulate the scenario that we have virtual threads being started by our server, what I have done is I have created a virtual thread from the JUnit method. So basically, all of this code is running in a virtual thread. So once we have customer, what do we do then? Then we are getting savings and loans data. For this, we need a scope because we want to wait for both of them to be finished. So we will create a new scope object, which is going to be structured task scope, and in this case, it's going to be shutdown on failure, right? Because we want both of the tasks to be finished. So what are the tasks? Let's fork them. Scope.fork, and we'll use customer util .get savings data. And this requires customer. This has to be a lambda. Okay, so we have savings data. Let's put that in task 1. And then we have task 2 for loans data. Okay, then we wait for both of them to be finished. Oh, not wait, but scope.join. And exception handling, of course. And then we propagate if there are any exceptions, so throw if failed. Okay, and now what we do, we can get the results from these tasks. So task1.get will give us the savings data. And then task 2 will give us loans data. And then we can use both of these to create a customer details object that we would need for calculate offer. So let's create that by passing in a customer, savings, and loans. Okay, and now in order to call calculate offer, okay, this is only one task, so we don't need scope. But what if we had multiple tasks here? Then we would have to create a new scope. So what we can do is we could do try and then scope 2. So this will be nested scope, and it is fine to do that. That we can have a new scope inside another scope and then have your subtasks started from there. But another interesting thing is that when you have your scope, which is used to fork some subtasks and then join them, you can reuse the same scope. So I could do scope.fork and then fork another task for the calculate offer part. So I can do this and then pass the customer details to it. And then there's only one task, so I'm just going to use scope.join and throw a failed. And let's put this in a task 3. And then task 3 dot get, which will give us the offer. And then we can print the offer. Okay, I assume we have now it complete. So let's run this and see if it exactly behaves the same way as compared to future implementation. So we have now first task running on one virtual thread when we have the customer, then we have savings and loans data, 2 tasks running parallelly on two more virtual threads. When we have their results, then we do calculate offer, which gives us that offer, and then we print it. So this is exactly what we wanted. This is exactly what we have. Now, the interesting thing is that here we have only one task, so we did not really require to create new scope or reuse the scope. So what we could have done simply is basically get the offer directly by calling this blocking method as if it is non-blocking. Right? So this would also do the same. So if I run this, we again have get customer running on one virtual thread, savings and loans data running parallelly. When we have them, then we have calculate offer, which gives us the offer. Okay, so this behaves exactly same as the complete future implementation. And if you compare these two, apart from the differences that we already discussed, one difference is that like we wanted to implement this structure, but it's not really evident from this implementation. But if you look at the structured concurrency implementation, you see that you have one task, and then you have scope, which creates two more tasks. And then once they are finished, then we continue with our final task. So basically, this structure is more clear in the structured concurrency implementation than the complete future implementation. OK, I also wanted to show a few more things. And I hope we have more than 5 minutes. Exactly 5. OK. So let's quickly see those things. So with structured concurrency API, right, you do 4 steps. So you first create a scope, then you fork your subtasks, you wait for them to finish, and then you get the results. So you have these tasks happening in this order, in this sequence. But the compiler doesn't really enforce you to follow that order. So what if you, say, miss joining them? And then you don't need to catch these exceptions. So compiler is not really pointing. So compiler is happy to for you to get these results. So if I run this, let's see what happens. Well, it throws an exception, which is owner did not join. So OK, you get the exception at runtime, but I think it would have been nice if the compiler really pointed you that you are missing something. And what if you you don't miss the join, but if you don't have any tasks forked? OK, of course, you can't get the results and anything. But the compiler, again, allows you to join the scope. Now let's see what happens if I do this. Well, there is no problem. And I think this is fine, because here you are basically saying that you want all of your subtasks to be finished. And in this case, you are finishing all the 0 subtasks successfully. So this is fine. Now let's try this with shutdown on success policy. So if you don't fork any subtasks, and you still want to join, now compiler is happily giving you results. That's a bit strange, right? You don't have any tasks forked, but you are able to get the result. So this would be interesting. Let's see what happens if you run this. OK, you get an exception, which is, I think, nice, right? You at least get some exception that you can't get the result from the shutdown on success scope when you don't have any tasks forked. But the exception is coming from shutdown on success.result. So join is happily joining, but result is giving you an exception when you don't have any tasks forked. That's it. I think these are the things that I wanted to show you. Let's go back to the presentation. So what we saw was shutdown policies, like shutdown on failure and shutdown on success. But you can also create custom shutdown policies. And that was the original question from you. So you can have your custom scope, and then you do whatever you want to do. Maybe you want to finish when 2 of the subtasks are finished, or 3, or some special combination of your subtasks. You can do all of that by extending structured task scope. And yeah, in general, if you are using virtual threads, be aware of pinning, because so pinning happens when your virtual thread is executing some synchronized code, or it is executing a native call. You can identify pin threads by using JFR. And in case of synchronized, it's only a problem if you're running long-running or blocking operations. So if it's like a really small, tiny thing that is happening inside synchronized, your application won't notice, so it won't be a problem. But in case it is a problem, you can replace it with reentrant locks. And in future, so synchronized will not pin your virtual thread. So then you don't have to worry anything about it. So that's it. That's all I wanted to show you. If you want to take a look at the source code, it's available on GitHub with this at this URL. And I work for ING, so there's quite a lot of interest happening at ING. If you're interested, you can scan this QR code. And yeah, if you have any questions, any feedback, anything, you can reach out to me here. And I want to mention one more thing. I have another talk if you are staying here for the entire conference on Wednesday. Again, it's actually exactly the same thing, but it is smaller format. So you only have some subset of information. Just giving you a heads up in case you show up there, and you will see the same slide, same information. But that's all. Yeah, thanks for joining, and enjoy the conference. Thank you.
Thank you very much, Balkrishna.
Thank you.
I think we should take time, or might take time, for 1 or 2 questions. Yeah.
So question, maybe more clarification. Yes, like virtual threads are released now, but structured concurrency is not yet released. As
Right.
far as I know, it will be Java 22. The plan is
Or
for
23,
that.
yeah.
Yeah.
Yeah, so the thing is that this is now, structured concurrency is available as preview. So you can experiment with it. So that's basically the idea right now. And when it is available in preview, you can still use it in production. So it is still production-grade code. The only thing is that it can change. The API can change. And then as long as you are ready to adapt to those changes, you can still use it in production. Yes?
Hi. Is there any reason to use a platform thread anymore, or should we just use virtual for everything?
Really good question. So virtual threads, their benefit is really evident if you have IO-bound tasks. So if you still have CPU-bound tasks, I would still say, why do you use virtual threads? I mean, it will not affect your application a lot. It might add little overhead. But then if you are already using platform threads, just continue using them as long as your tasks are CPU-bound. But for IO-bound, I would definitely recommend to use virtual threads.
Thank you for presentation. Just a question.
Yeah.
Is there any retry logic embedded in the API? For example, if task is failing, I want to retry n times.
Yeah, good question. So it's not there in the API that is available right now. But what you would typically expect is that on top of the current API, you can expect some extra concurrency libraries being created in the Java ecosystem, which we would provide these kind of mechanisms. In fact, structured concurrency API makes it really easy to extend the structured task scope and implement your own logic for retries and failsafe. So those you can expect in those different libraries.
Okay, first of all, congratulations for your presentation.
Thank you.
And I have a little question. And okay, virtual threads makes us to see reactive programming something boring stuff, because we are familiar with imperative style. What do you think about that? Reactive programming and imperative programming could be coexist with virtual threads. What do you think about that?
Yeah, OK, so good question. So the thing is that I think reactive programming and imperative programming, they are different paradigms. And they would both, in my opinion, they would both still coexist because they are, let's say, solutions to different problems. If your domain really has the need for having reactive systems, then you would really want to use reactive programming to implement that, because then your domain represents exactly that thing. But if you're just using reactive in order to gain CPU out of your system, then again, you will stop using that, right? So some of these use cases where we are using reactive just to gain more CPU efficiency, we would stop using that, and you would replace that with virtual threads. But if your domain is highly reactive, it is embedded in the nature of your domain, then you would use reactive programming to implement those. So in my opinion, it would still coexist. And I can expect that the reactive libraries to use virtual threads and Loom underneath.
So we will stop here, but you should definitely not follow up these conversations between each other. Thank you very much, Balkrishna.
Thanks for having me, and thank you all for listening. Thanks.